next slide. So now here is an outline showing the M for the chapter. So we wanted to know what is actually a distance protection is that we use in a power system networks. So in the first subtopics, I will talk about why there's a need of distance protections, what will be its working concept. Then only we'll proceed to the next topics here will be on the network's impedance diagrams. So network's impedance diagram, also known as RX diagram, so its purpose is used to represent the impedance of any elements we can find in the power system network. So from there, we can actually use this network's impedance diagram to analyze whether we have a healthy system or we have a faulty systems. And at the same time, you can also use this RX diagram here to set the working zones of different types of distance relay we have. After this, we'll start to talk about the basic working principles of different types of distance relay we have. For example, we are actually focusing on the simple impedance relays, the most simplest one, followed by the reactance relays, and the most commonly used types of distance relay we also have known as the Morse relay. So this is also known as the admittance relays. So as usual, we will end the chapters by talking about what is the possible problems might be faced whenever we are implementing the distance protections in the power system networks. So now let's move on to the next slide here. So I will brief you what is the lesson learning outcome for these chapters. All right, so there are totally 4 lesson learning outcomes. The first one is to understand the concept of the distance protection. So for information, distance protection is actually operate based on the basics Ohm's law. And after this, we will try to discuss what is the difference between if we are applying the overcurrents relay and the distance relay. So from that, we can justify why distance relay is much more suitable whenever we want to protect the transmissions line. And following the next one we have is to learn how to analyze the power system networks, whether we have faults or healthy conditions by using the impedance diagrams. And the last one here is to understand the working principles of different types of distance relays we have and what would be their limitations. All right, so this is what you can bring back after I have completed these chapters. All right, so now before we go in depth of understanding different types of distance relay we can use in the power system networks, we need to know what actually is for this distance protections. So for this distance protection, you refer to the first bullet point, is actually used to detect or to identify the positions of the fault by monitoring the impedance of the faulty point which has been seen by the protective relays. So in addition to sense we have fault within the system, it can also tell you exactly where does this fault occurs whenever we have fault happens. All right, so usually we will have these distance protections work as the primary protections for the long distance of transmissions line, while we will have it as a backup for different components you can find in a power system network, such as the machines like the generators, the transformer, as well as the auto transformer. So auto transformers here is actually a kind of transformer which consists only of one winding shared between the primary side and the secondary side. So this is actually same as the power transfer. It can be used as step up or step down transfer, which offer no interference or disturbance to the system. All right, now let's refer to an examples here where we have a very simple networks, how actually we can implement the distance protection and how it looks. So let's say we have a transmissions line, and this line has been fed with 2 generation sources at both ends. And right now, this line has been divided into 3 different zones, where the substations here, and each zones will have been implemented with its own respective scheme. All right, this is actually the protection scheme. So let's say right now we have this look as the distance relay. So we are implementing the distance relay here at the beginning of the transmissions line. So what happens if I have fault occurs at this point, right, with the positions at F1s here? So for this distance relay, so you draw a vertical line like this, you're actually able to measure the distance of this fault location. So it will return you D1. Where does this first fault occur? So what happens if I change the fault position to the sender zones of the transmissions line? So same based on its relaying point here. So starting measure from its point up to this 40 point, it will return you D2 as the fault positions for the second fault right now, which occurs at the sender zones of the transmissions line. So same ideas apply to the third fault here, which occurring at the ends of the transmission line. So it will return you D3 this time, telling you where does it occurs. All right, so this image is actually showing you how does the actual distance relays looks like. So here is the front panels where allow us to do the adjustment to set up the pickup impedance setting for different zones of projections. So here we have the input ports and output ports here where we have the ports that allow us to connect with the voltage transformers and current transformers so that we can get voltage and current reading. So from there, we can measure what would be the impedance of this for this point. All right, so now let's move to the next slide here to see how does it work, all right, by examining the basic principles of the distance projections. So with the fact that every power line is actually evenly distributed with the resistance and reactance value. So now how long would be the higher the length would be for this power line, the impedance value will be higher. So every cam we will know what will be the resistance and reactance value. And this resistance and especially for reactance value actually change based on the design as well as the constructions of the power transmission. So remember what we have learned from the previous course, how you arrange the wire, the reactance, which is the inductance and capacitance value for the light actually will change greatly. And usually this total impedance value will be given in the functions of length or in distance. So like let's say every cam, how much in terms of impedance we could have for this transmissions line. So right now, distance relay is actually make use of this fact to calculate where does the fault location is. So basically, it's operate based on the basics of Ohm's law. So which means that it will need to measure what is the voltage value and current value. So by using the Ohm's law here to calculate the impedance that's being seen by it, all right? So by dividing the voltage and current value, so it will able to calculate what would be the impedance of the 40 point. All right, so now let's check out this diagram here, how actually we can implement the distance relay. So let's say this is a transmission line we want to implement with the distance projections, and it have its own impedance value. So it have its own resistance value as well as the reactance value. All right, so whenever we want to implement the distance relay, we need to get two reading, the voltage reading and current reading. So with such a case, we need to install the voltage transfer in parallel connection, which is across these substations here to get the voltage reading. At the same time, we will use the current transfer, connect in series with these transmissions line so that we're able to get the current readings. All right, so after it getting the reading from both current transformers and voltage transformer, so it will implement this. So dividing the voltage and current value. So to see what is the impedance value seen by it right now. So in the event, if the total impedance calculate is actually lesser than the pickup impedance value, usually we set at the transmissions line impedance, that means that it's recognized as a fault occurs. So this distance relay will start to issue the triggering command to the breaker. So that's how we isolate the faulty lines up by using the distance relay. Okay, so now the distance protection is actually operate based on the fact that whenever the impedance value calculated is high, this indicate that there's no fault occurred from the protected line unit. But in the event, if you divide the voltage and currents, the impedance value is low instead. So this time it recognized that its fault occurred. So to use this fact and explain how actually is detect the fault, so let's see we have two different cases. So we start with healthy transmissions line first, which is with no faults at all. So now we have no faults, right? This is the line that we want to protect with the distance relay. All right, so the total impedance seen by the relays right now would be the transmission line impedance together with the load impedance. As we know, the transmission line is actually sending the power to a certain source, right? So the total impedance since right now will be very high because line impedance add with load impedance, right? So during these situations, the measured currents by the current transfer also is the rated current flow. So now this distance received such high impedance value. So it say this time we have no fault occurs within the networks right now. So what happens if I have fault occurs? Let's say I have short circuit conditions that occur at this specific point of the transmission line. So now during these moments of times, right, the transmission line will be divided into two different sections. The first sections, the line impedance can be seen by the relay. And another section here is the unseen part, which consists of the another part of the transmission line act with the load impedance value. So this is the path which is unable to be seen by this distance relay. Why? Because we have a short circuit occurs here. So the current flows right now will be high, which can be measured by the fault current due to the low resistive path. So the current will tend to flow through the short circuit point. So that's how this path is being shorted, unable to be seen by the distance relay. So right now, this distance relay divide the voltage and current value. So the impedance value is just this part. So the impedance value is low right now. So that's how this distance relay recognizes as the fault occurs within the system. So it starts to send the tripping commands to the breakers. Okay, so that's how it works based on this fact. Whenever impedance is high, it's normal. All right, so whenever impedance drop due to the fault occurs, so that's how it's recognized or identified as fault situations. All right, so let's move on here to the next slide here. So I will start to talk about the physical constructions of the distance relay. So if you open up the distance relay and look inside, right? So this is the components that you can find. So it consists of a balancing beam with a set of coin here. All right, one is known as the restraining coin. Another one is the operating coin. So these two coin is responsible to control this balancing beam, where this balancing beam is carrying the movable contact, and this is the fixed contact. So what happens during normal conditions? This balancing beam is actually like this flat normal situations. So now these two are unable to form a close connection. So this telling you that the tripping circuit is actually not complete. So that's how the distance rate not work whenever we have normal situations. But what happens if we have fault? So during the time we have fault, this measure current by the current transformer, it will actually send into this coil here. We call it as the operating coil. So whenever current flowing through the coil is become magnetized, so it will generate the operating torque. Right? So under these situations, the voltage measure is actually low. So now the restraining coil, which is responsible to generate the restraining torque, the restraining torque is lesser than the operating torque. So now this time, it will create a force that attract this balancing beam. So this balancing beam become tilted, and that's how these two contacts form a close connections during abnormal situations. So it will start to send the tripping command to the breakers. So right now, as being mentioned, we have two coils. One is restraining coil, another one is operating coil. The measured voltage from the voltage transformer will feed into the restraining coil, which is responsible to give you the restraining torque. While the current transfer, the measured current will feed into the operating coil, so is responsible to give you the operating torque. All right, so as a fast recap for you, so just I already explained that. So during healthy conditions, so now how actually is worked by looking into the components of the distance relay. So whenever we have healthy situations, the measured voltage value is actually much bigger than the current value. Okay, so now which means that the restraining torque is actually much more higher as comparing to operating beam torque. So under this situation, we will have balanced beam situations, though the contact remains open. So the tripping circuit unable to form a close connections. That is for healthy conditions. What happens if we have fault situations? Obviously, the short circuit current is much more bigger if we comparing with the measured voltage value. So this in turn will cause the operating torque much bigger than the restraining torque. So right now, the balancing being unable to be balanced. Right now, we have a tilt situations. That's how we have a close connection for the tripping circuits, and the commands will send to the breakers to operate to trip the transmissions line. So that's how it works under both these two different situations. So take note that seeing as we have the operating coil as well as a restraining coil, so the numbers of turns will actually allow us to change or adjust the optics reach of the relay, which is actually I want to change different pickup impedance value for this relays, right? So by changing numbers of turns, or I should say the ampere turns relationship between the restraining coil as well as the operating coil, are able to adjust the pickup impedance value. Okay, so let's have this distance relay to have a complete connections with the transmissions line that I want to protect with the distance relay. All right, so this is the line I want to protect. So in order to implement the distance protections, I need both CT and PT, the current transformer, and voltage, or I should say the potential transformer, connect across the bus bar or the substations, current transformer in series with the transmissions line. All right, so this measured current value will send into the current coil, or I should say the operating coil here. So it's actually representing the operating torque, whereby for the voltage transformers here is actually feeding the measured voltage value from these substations to this side here, all right, which is to the voltage coil, or I should say the restraining coil here. So this voltage value is responsible for the distance relay to generate the restraining torque. So in the event if I have fault situations like a short circuit occurs within the transmissions line, so this distance relay will start to measure the impedance values of this 40 point by dividing the voltage and current value. So in the event if these impedance values start to drop, which indicate that the measured voltage value is actually lesser than the current value, and this impedance measured by the distance rate is, let's say, less than the pickup value or the settings value of this distance relay. So this distance relay will start to operate to trip this 40 line. Okay, so now let's move on here to talk about the distance relay, how actually it gives you the positions value. All right, so remember the line impedance, how much is it, is actually based on how long will be for your transmissions line. They are directly proportional to each others. Right, so the longer the length will be, the higher the line impedance value. And we are using these properties here to tell you where does the fault occurs in terms of positions, measuring start from the relay positions. All right, so let's see back this simple power networks here where we have implemented the beginnings of the line here with distance relay. All right, so if this transmissions line giving me every km here, I will have 0.1 ohms. So right now we'll use this fact here to calculate where does this 3 faults occurs at different locations of the transmission line. So for example, for the first fault here, it start to divide the measured voltage value and the current value. And then the measured impedance of the first 40 point is actually 4 ohm. So same for the second fault here that occurs at the center zones here. So divide voltage and current, I get the value of 6 ohm. And the last fault here at the ends of the line, let's say the measured impedance values that's seen by this distance relay is actually 10 ohm. So by using this fact, I can actually calculate where does this different faults occurs. So now I know that every km I have 0.1 ohm. So with the measured impedance value, if I divide with this, I can actually get what is the positions of the first fault. So by having 4 divide with 0.1, so I know that the first fault here is actually occur 40 km away from the distance relay. So that's how I detect the fault positions. So same concept apply for the second fault here with the measured impedance of 6 ohm. So you divide with 0.1 ohm. So I can tell you that from these relaying positions, the second fault is occur 60 km away. And same goes for the last fault by having 10 divided with 0.1. So I know that the last fault is actually at 100 km away from this distance relay. So here you can see, right, whenever the measured impedance value is high, so this is actually telling you that the fault is occur further away from this distance relay, or reversely, if you refer to this box here, whenever the measured impedance value is low, like this case here, so we know that this fault is actually occur closer to the distance relay. Okay, so now let's see how actually we can do the setting for the distance relay. So there's one important point we have to take note on, whereby the measured impedance by the distance relay is not the actual values of the transmissions line. Why? Because this measured impedance value is actually calculated based on the current value and voltage value that obtained from the instrumental transformer that feeding to this relay here. So if you refer to this image, let's say this is the transmission line I want to protect. So I have a distance relay here. I'm getting the current measurements from this CT and voltage measurement from this VT. So whenever I divide the voltage and the current value, the calculated impedance value would be the secondary impedance value of this transmission line. So it's not the actual value for the transmission line that I want to protect. But if I want to do the setting for this distance relay, is actually operate based on its secondary value. So how actually I can implement the setting? So usually we will know what is the primary impedance for the transmission line. So I will need to convert this primary impedance value into its secondary form. Then only I can perform the setting for this distance relay. So how I can do this is by applying this formulas here. So you have to memorize this. So having the transmission line impedance multiplied with the ratios of CTR and VTR. So current transverse ratios divided with voltage transverse ratios multiply with the line impedance here. That's how we do the conversion from the primary impedance into a secondary form. Right, so that's how we can do the setting for the distance relay. Okay, so now let's see some of the advantages of using distance relay, why it is much more suitable, especially for long distance of transmissions line. So let's say we have this network, the line that's being divided into 3 sections with the substations, and then we are feeding this line with the generation slots at both ends. Okay, so each sections of the line I have implements with a pair of relays labeled as R1, R2, R3 up to R6 here. And seeing as the relay at the top, we have the arrow, right, pointing to the sensing direction. So we know that all of this relay here is with directional features, all right? It's able to sense where does the fault occurs. So for example, R1, R3, R5, with the arrow pointing to the right, they are actually able to sense those faults that locate at its right-hand side, whereby for R6, R4, and R2 here with arrow pointing to the left. So there are the relays that are able to detect those faults that locate at its left-hand side instead. So what happens if I have fault occurs at the center zones of the transmission line? So this time, those relays that are able to detect, there are those marked in red colors, which is R3, R4, and R1 and R6. So let's say I'm using the overcurrent relay. So under these situations, those that has been marked in red colors, right, will actually take action to break the circuit. So which means that we have the continuity of power supply for the entire network is being lost right now. So why we say that supposedly we have R3, R4 that locates within these zones, whereby it should recognize this is the internal fault to take actions will be sufficient. But then for R1, R6 here, so this is actually considered as an external fault. So it should not trip to break these fault situations. So right now we have a situations where overcurrents really unable to sense the fault positions. Let's say it doesn't being implemented with proper times delays. So it will take actions to cause the entire network become shut down. So that is the problems of overcurrents relay for the distance protections. All right, so now let's say we change the relays right now. Instead, we are using overcurrents relay. We are using distance relay for the same situation, means that R1, R2 up to R6 right now, we are having the distance relay. So we know that the distance relay will actually measure the fault positions, right, or the fault distance. And then it's use this positions distance here to identify whether this fault is actually the internal fault or the external fault. So as we know, right, R1, R3, R4, and R6 is the one that able to detect this fault. So now initially we have these R3, R4 here start to measure the positions from its relaying positions. So right now, these two relay will recognize that this fault is actually occurs within the zones because the return distance is low. So it will start to take action to trip the networks. But for the analyst relay here, we know that R1, R6 also able to detect this fault. But this time, whenever is measured, the distance is much more higher. So it know that this is actually the external fault. So which means that R1, R6 will not work. So in this way, only the middle zone will being turned off, while the another two zones here will continue to have power supply. So we are managed to conserve the power flows of continuities by using the distance relay. So that is the basic list of the advantages of distance relay as comparing to overcurrent relay. So you might ask now, what happens if these R3, R4 fails to protect the networks as a primary protection, seen as the fault is occurs within the zones of operations? So we know that our R6 also able to detect it, right? So there must be a coordinations among these different distance relay we have in the networks. So right now, this R1, R6 will actually send this fault and works as the backup protections. Okay, so we can actually have distance relay to work as both primary protections as well as backup protections as same as the overcurrent relay. So one more issue faced by the overcurrent relay, let's say we use it for the long transmissions like with weak generation source. So the fault must be unable to be sent if we are using overcurrent relay. Why? Because the fault current might be too low right now. So to further explain this, so let's see what happens. I have a long distance of transmissions line. So it's being fed with, let's say, with a weak generation source. I'm using the overcurrent relays right now. So whenever I have the weak generation source, do you still remember? The impedance imposed by this weak generation source is actually much more higher. All right. So under these situations, if I'm using overcurrent relay here, this overcurrent relay can only able to protect these transmissions like up to point B1 only. So how I know this? So let's say I plot the fault currents with respect to the distance from this overcurrent relay. So if I have weak generation source, the impedance value is high, right? So now whenever the impedance value is high, let's say I want to calculate the fault currents, I will have the voltage divided with impedance. So if I have the voltage divided with the impedance, which is high, so the fault current is actually much more lower. So let's say at this point here, okay? So yes, at this point, the overcurrents the relay able to detect. So let's say if I shift the 40 point away from this overcurrent relay, so which means that further away, the impedance from the line will actually build up the overall impedance. So the impedance is getting higher and higher Fi as when I move the 40 points away. So at the same time, the 40 current is also getting lower and lower. So let's say I set this as the pickup current value for this relay. So you will notice that for this overcurrent relay can only able to pick up the fault up to this point only. Why? Because if I continue to move further away from the 40 point, the fault impedance value, the fault current value is getting lower and lower, which is lower than the pickup settings of this overcurrent relay. So what happens if I change the generation source, which is much more stronger? So if I have stronger generation source, the impedance is much more lower. Let's say the generation source impedance is ZS1, all right? So if I find the fault current by having the voltage divided with the low impedance value, so the fault current is much more higher. So say I start to move the 40 point away from this overcurrent relay, so you can see the transmissions line impedance build up the overall impedance. So the fault current is getting lesser and lesser. But this time, if I have stronger generation source, this overcurrent rate can detect the fault which is further away as comparing to the first situations here. It can reach up to point B3. So which means that for the fault occurs up to B3 here, this overcurrent rate able to detect only in the event if the generation source here is strong. Okay, so now you can see this overcurrent rate is actually depending on this. Is it having a weak generation source or are we having a strong generation source? So it will tell you the different point where this overcurrent rate can reach to pick up the fault situations. So from here, it motivates us to use the distance relay. Why? Because distance relay is operation doesn't change based on this generator's characteristics. Right? So regardless we have weak or strong generation source, based on the pickup impedance value you have been set, so it able to reach up to that point. Okay? So that's why for the long distance of transmission side, especially with weak generation source, distance relay is more suitable as comparing to overcurrent relay. Okay, so now let's see how actually we can do the setting for the distance relay. So for distance relay, it has been set to operate up to specific values of impedance. So there are two forms of setting for a distance relay. One is known as underreaching setting. Another one is known as overreaching setting. So what is the difference between these two? So the tendency of reach for a distance relay which has been set to not operate at the preset value, especially for the fault that locate at the remote locations of the protected line. That is what we call it as the underreaching setting. So usually underreaching setting has been set as the primary protections. So similarly, we have overreaching settings. So this time is the tendency of reach for a distance rate, whereby to operate at the impedance, which is much more higher, or I should say, for the fault that occurs beyond the next terminals here. This is what we call as the overreaching settings of the relay. So usually overreaching settings for the distance relay has been used as the backup protections. So to further explain this, I have drawn these diagrams. So now, how I know now I having a primary protection, so I want to do the underreaching setting or the overreaching setting. So let's say this is a line that fit by this generation source, and I have two zones right now. So let's say I'm using a distance relay. So this distance relay is responsible to protect these sections of the transmission line as the primary protections. So for underreaching settings, so given a terminal, so which is given the line that you want to protect, you set it do not operate for those faults at the remote location, which is at these sections of the line here. So you can see instead of 100% of this line to be set for this distance relay, I have purposely set can be reached up to this point only. That's why we call it as an underreaching setting. So for underreaching setting is for this distance relay as the primary protection for this part of the transmission line. So how about overreaching settings? So instead that the distance relay will operate for those faults that occurs beyond the next terminal. So now this is the distance relay. So this is the line is responsible to work for as a primary protection, and it should be worked as a backup for a next line sections, correct? So right now I set it to be overreach until the next terminals here. So this is what we have as the overreaching settings. So as you can see, next line section. So this is basically how to say pick up by this distance rate but as a backup protections. Okay, so we have both under-reaching setting and over-reaching setting for distance rate. And because of this, we can have different zones of protections for the distance relay. All right, so let's see some points here. So generally distance relay, all right, the zone is being set to opens at the far. This means that we have under-reaching setting for the distance relay, right? Why we do so, all right? Or in other words, the remote point of the reach for a distance rate is actually cannot be exactly determined. So which means whenever we have the far end 40 point, so by dividing the voltage and current value, the impedance calculate is actually not accurate. So some uncertainty about the exact reach for the far end 40 must be accepted. All right. So in such a case, underreach has been purposely chosen so that we can avoid the overreaching to the next slide section to ensure good selectivity due to these three reasons here. So now, why we have underreaching setting for the primary protection? First, it's not practical to able to measure the impedance values correctly, especially for the very long distance of transmissions. Let's say we have 100 km long. So obviously, the impedance calculation is not correct. So with such a case, survey length are usually used and we could have error up to 10%. And the second reason here is actually coming from the instrumental transformer. So this current and voltage are unable to measure the voltage values or the current value correctly for the far end 40 point. All right, so with such a case, that is error present. That's why these two is interlinked to each others. And the third reason here is due to the limitation from the manufacturer's tolerance, whereby the distance relay abilities to measure the impedance correctly at the far end point of the transmissions line. Right, so this is the three reasons why we have set to be under reach for the distance relay that would as the primary protections. All right, so now for distance relay, we could have three zones of protection for this syllabus. On the year three, we can have much more. But for this syllabus, we only cover up to three zones. So we have zone 1, zone 2, and zone 3. So what is the difference between them? So we can refer to these tables here. So for zone 1, right, the protection coverage for the distance rate has been set to be about 80% of the transmissions line that you want to protect. So you can see here is under reaching setting. So we have zone 1 setting for the distance rate to be looked as the primary protections. So how about for zone 2? So this time, the protections coverage range is actually much more larger as compared to first sections or first zones. So it's covering the entire first line sections and with additional about 50% of the next line section. So you can see overreaching setting. So you can tell, right, zone 2 is actually looked as the backup for the zone 1 relay. All right. So that is basically what we have for the zone 2. So how about for zone 3? Now the protection coverage will be the largest, whereby the entire line section plus additional 120 up to 180% of the next line section. So you can see zone 3 has been set to be overreach as well, and it could be looked as the backup for zone 2 relay as well. All right, so it can reach up to the next line sections. Okay, so because we have different zones of protection for the distance relay, each of them having a different functions, some work as primary, some work as backup protections. So with such a case, the time coordination is very important for each zones. So usually we will have the time margin or the delays of time for each relay that work as a backup to be wait at about 0.3 seconds. All right. So which means that before zone 2 start to react, yes, it's detect the fault. So it will give 0.3 seconds for this zone 1 relay to work first as a primary protections. Okay. So for those relay that should work as a backup, is only true, which means that it's only feasible to pick up the fault that at neighboring line here, depending on how far it can be reached. Is it 50% or even longer? So this zone 2 can work as the backup protection. All right. So for coordination purpose, each zone has to be graded according to the primary zone. So for example, zone 3 has to be coordinated in both time and distance from the second zone, whereby for the second zone has to be graded according to the zone 1 setting. All right, so now let's move on to next slide here. So how actually we can set different zone for a distance relay that work as a primary and backup protection. So let's look into this sample power system network. All right, so now we have a transmission line which feed by the generation source at both ends after the transformer. And this transmission line split into 3 sections where the substation A, B, C, D. Okay, and each section here have implements with a pair of distance relay R1, R2, R3 up to R6. And you can see, right, they come with directional feature. So we know R1, R3, R5 are those distance relay able to sense the fault that locate at its right hand side. R6, R4, and R2 here with arrow pointing to the left. So there are the distance relay able to detect those fault at its left hand side. All right, so you can actually see their step characteristic in this diagram here. So the y-axis is actually showing its operations time, and the x-axis here is actually showing the distance, all right, of the how far away for the fault occur from the distance relay. Okay, so now regarding to the zone setting for a distance relay, so let's refer for relay 1 first. So I know that this relay 1 is responsible to protect the line between A and B as a primary protection, is correct? So the first zone setting, if you go back to the descriptions here, it say that it's covered about 80% of the line sections I want to protect. So now this is 100% of the line from A to B, right? So this relay 1 set up to 80% of the transmissions line I want to protect. So this is the reach of relay 1 here. So let's say any fault occurs within this 80% of line sections AB, it will be picked up by this relay 1 as a primary protection. So we have under reaching settings. How about for zone 2 setting of this relay 1? So now, do you still remember? It will wait for 0.3 second delay. So wait for 0.3 second. I will have second zone setting. So let's say I have the second zone setting covering the first line section plus additional 50% of the next line section. So next line section will be BC. So entire first line section plus 50% of the next line section. So this will be the second zone setting of relay 1. So you can see relay 1 will as the backup for the fault occurs within next 50% of the transmissions line, right? So that's how we have zone 2 setting. So how about zone 3 setting for relay 1? So the coverage areas will be the largest. So now is entire line section plus additional, let's say 120% of the next line sections. So 100% plus another 120, so another 120% of the next line section. So you can see this will be the third zone setting of relay 1, work as a backup for this section up to these sections of the next line section. So you can see, right, the delays of time will be even more larger. So after 0.3, you will need to wait another 0.3 seconds. Then this relay 1 work as the backup for these sections of the transmissions line. So that's how we have set different zone setting for the relay. All right. So this is zone 1, zone 2, zone 3 setting for relay 1. So how about relay 3? Same. Zone 1, 80%. Zone 2 is 150%, next line sections. And this is a zone 3 setting of this relay 3. And here is for relay 5. Same applies for those relays that are able to sense those faults that occur at its left-hand side. So if you take R6 here as an example, responsible to protect the line section C and D. So 80% of the transmissions line. So this is the first zone setting, relay 0.3, second zone setting for relay 6, and this is the third zone setting. All right. So same goes for relay 4 for this one, and this one is for relay 2. Okay. So now let's simulate a fault occurs within the transmissions line. So let's say at this X point here, we have short circuit occurs between the substations B and C. So which relay will actually trigger that? So under these situations, whenever we have this fault occurs, we know R3, R4, R1, R6 able to detect it. All right. So let's draw a vertical line here to indicate the fault positions. So you found that this fault is actually fall as the first zones of both relay R3 and R4. So which means that for these two relay, it will work as the primary protection to trip this fault without any time delay. All right. So now what happens if this R4 doesn't take action or this R3 doesn't take actions? So let's refer the one at the left-hand side first. All right. So if R3 doesn't work, all right, as a primary protections, we know that we have backup coming from R1, right? So, and you can see this fault is actually fall as second zones of relay 1, okay? So you will know that after the delays of 0.3 seconds, this relay 1 will trip as a backup protection for this fault, right? So how about if I have R4 fails to trip as a primary protections? So right now, I know R6 able to detect this fault, but this fault is fall as the third zone setting of relay 6, correct? So which means that I have much more longer time delay, 0.3 at another 0.3 seconds. So yeah, in the event I have this fault occur and R4 doesn't take actions, I have backup coming from relay 6, but it has to wait up to 0.6 seconds first. Then only I will able to trip this fault occur. Okay, so that's how it works. All right, so now this relay is very famous as a primary protection for the transmissions line due to the advantages here. First is because the zones of protection is actually depending on the impedance of the line that we want to protect, which is constant. And at the same time, we know that to measure the impedance value, we are actually getting the voltage and currents value from the instrumental transformer. So it's actually virtually independent on the magnitudes of the voltage and the current. But it has some problems due to both under-ranging setting and over-ranging settings for the distance relay, especially we have long distance of transmissions line. So under these situations, we have this issue whereby the distance relay fails to recognize whether this fault is occurred at the ends of the line sections that I want to protect, or is it the fault that occurs at the beginning of the next line sections. But this problem can be resolved by using the 3-zone setting for the distance relay by having 3 distance relay at the same terminal. So which means that here you are using 3 relays, right? With first, second, and third zone setting is not 1 relay, but 3 distance relay to solve these problems. All right. So now I will show you a short videos here talking about why we want to have the transmissions line being protected by using distance relay, but not other relays. All right. I hope that it can help you to revise a bit about this. And after this, that only will take 5 minutes break. I can't hear the voice. So let me play through the Chrome tab. Wait,
Thanks for taking the time to watch the first video in our end-to-end testing series. End-to-end testing builds on traditional transmission line protection. So we're going to start with some basic principles from the Relay Testing Handbook series to make sure everyone is on the same page before we delve into the end-to-end testing details in future videos. Power lines transmit energy from one location to another and are the lifeblood of the electrical system. There are many problems that can cause a power line to fail, such as lightning strikes, animals spanning two lines, equipment failure, or just plain human error. Your traditional overcurrent protection worked well when the power flowed in only one direction because the fault can be located by current magnitude. The relay closest to the fault will trip first in a properly coordinated system because of the large current flowing into it and its smaller pickup setting. Current can flow in any direction on an electrical grid, so it's almost impossible to set all of the relays to operate correctly for every possible scenario. Even if you were to achieve the impossible and set every relay perfectly, everything would get thrown out of whack the next time the grid is changed to add a new generator or customer. Imagine that you're a utility design engineer in the dirty 30s, and you keep losing the entire electrical grid for every fault, no matter where it is on the grid. What you really need is a relay that will operate for any fault on the transmission line it's protecting, and ignore faults anywhere else on the grid. You can measure the voltage at any point in the system using PTs, and you can also measure the current entering and leaving the power line with CTs mounted at each end. You can use the current and voltage with your standard electrical formulas to calculate phase current, residual current, phase voltage, residual voltage, directional overcurrent, power, resistance and impedance, any symmetrical component, or differential current. Will any of these values help you determine whether a fault is on the transmission line or not? We already know that overcurrent and voltage elements are not selective enough for this application. Symmetrical components are mostly extensions of current and voltage that are good at identifying what kind of fault occurred, but not where the fault is. Power and directional overcurrent will tell us what direction the fault is, but they're not selective enough to determine if the fault is on the power line or somewhere further down in the system. The perfect solution is differential protection. Differential protection monitors the current entering and leaving the transmission line and sums them together. If the currents cancel each other out, the differential relay will not trip because the system is either operating normally or there's a fault that's not on the transmission line. If the current and voltage leaving the transmission line do not cancel each other out, the fault must be on the transmission line, and the relay will open both circuit breakers. This looks like a great solution. Too bad this is the 1930s, and the technology necessary to transmit three-phase analog signals across large distances in real time doesn't exist. That leaves you with impedance, which is a pretty good second-best solution. In order for this solution to work, you need to know the impedance of the transmission line. You could measure it with fancy equipment, but it's usually easier to calculate it using size of the wire, length of the transmission line, and spacing between wires. Let's imagine that we've run through the calculations, and miraculously, the spacing and type of wire works out to 1 ohm per mile. The transmission line you want to protect is 10 miles long, so the entire impedance of this line is 10 ohms. If we applied a dead short at the end of this line, the relay would measure the voltage and current flowing through the relay, apply Ohm's law, and calculate 10 ohms. If there was a fault 50% down the line, the relay would measure 5 ohms. You've come up with a great solution to the problem that can be applied to any transmission line as long as you can calculate the line impedance. You've gone into your workshop with this information and created an impedance relay that will only look for faults in the forward direction. Your creation has an adjustable pickup system so that you can apply this relay to any transmission line. And now it needs a setting for the 10 ohm power line we started with. What pickup setting in ohms will provide the best protection for this transmission line. Did you choose 10 ohms? That's a great setting for a perfect transmission line in a textbook. Unfortunately, we live in the real world, and there are a couple of problems with a setting set to 100% of the transmission line. The first problem is that we calculated the transmission line impedance, and there will always be errors and assumptions that will affect the calculations. Even if we could account for the inherent inaccuracy with the calculations, the transmission line impedance will change with temperature and spacing between wires. Seasons and wind can change the transmission line impedance. What signals are you using to measure the real-time impedance? Those CTs and PTs aren't perfect, especially the CTs. What is the standard percent error allowable for protection class CTs? If you guessed 10%, you're correct, up to a point. Protection class CTs can have errors up to 20% when the current exceeds 20 times its rating. All of these problems add up, and if we set the impedance protection to be 100% of the transmission line, the real-world impedance may be larger or smaller than our calculations. If the real impedance is smaller than our setting, our relay may trip for a fault on an adjacent